Part 8.
I mean, as it is, as I said, like China's like probably just twice as much refining as the rest of the world combined.
Yeah.
So if you go, if you just go down to like fourth and fifth tier supply chain stuff, like at the base level, we've got energy, then you've got mining and refining. Those foundation layers are, like I said, China, as a rough guess, China's doing twice as much refining as the rest of the world combined. So any given thing is going to have Chinese content because China's doing twice as much refining work as the rest of the world. And then they'll go all the way to the finished product with the cars. I mean, China's a powerhouse. I mean, I think this year China will exceed 3 times U.S. electricity output. And like electricity output is a reasonable proxy for, for the economy. So like in order to run the factories and run everything, you need electricity. So electricity is a good proxy for the real economy. And so if China passes 3 times the U.S. electricity output, it means that its industrial capacity, as a rough approximation, is 3 times that, will be 3 times that of the U.S.
Reading between the lines, it sounds like what you're sort of saying is, absent some sort of humanoid recursive miracle in the next few years, on the sort of like whole manufacturing, energy, raw materials chain, like China will just like dominate, whether it comes to like AI or manufacturing EVs or manufacturing humanoids.
In the absence of breakthrough innovations in the U.S., China will utterly dominate.
Interesting.
Yes.
Robotics being the main breakthrough innovation.
Well, if you do, like to scale AI in space, like basically need
Space.
you need the humanoid robots, you need real world AI, you need a million tons a year to orbit. Like let's just say, like if we get the mass driver on the moon going, my favorite thing, then I think
We'll have solved all our problems.
yeah. So this is like, I call that winning.
So,
I call that winning. Big time.
You would finally be satisfied you've done something.
Yes.
You have the mass driver on the moon.
That's right. I just want to see that thing in operation.
Was that out of some sci-fi, or where did you...
Well, actually, there is a Heinlein book. The moon is a harsh mistress.
Okay, yeah, but that's slightly different. That's a gravity slingshot, or...
No, they have a mass driver on the moon.
Okay, yeah. But they use that to attack Earth, so maybe it's not the
They use
greatest...
that to assert their independence. from
Exactly.
Earth.
What are your plans for the mass driver on the moon?
They asserted their independence. The Earth government disagreed, and they lobbed things until the Earth government agreed.
That book is a hoot. I found that book much better than his other one that everyone reads, Stranger in a Strange Land.
Yeah, Grok comes from Stranger in a Strange Land.
Yeah, but I much prefer...
Yeah, the first 2/3 of Stranger in a Strange Land are good, and then it gets very weird in the third portion.
Yeah.
But there's still some good concepts in there.
Yeah.
Labelbox can get you robotics and RL data at scale. Take robotics. Let's say you need 100,000 hours of egocentric video. Labelbox starts by helping you define your ideal data distribution. Like for
Hours and days, impossible.
where they can film for
Managing
the highest quality
for managing people. Like, you interviewed the first few thousand of SpaceX employees and
Yeah.
lots of other companies. What is...
Obviously, it doesn't scale.
Well, yes, but what doesn't scale?
Me. I mean,
Sure. I know that, but like, what are you looking for?
I mean, literally, it's not enough hours in a day. It's impossible.
But what are you looking for that someone else who's good at interviewing and hiring people? What's the je ne sais quoi?
Well, at this point, I think I've got. I might have more training data on evaluating technical talent, especially, but talent of all kinds, I suppose. But technical talent, especially, given that I've done so many technical interviews and then seen the results. Technical interviews, seen the results. So my training set is enormous and has a very wide range. Generally, the thing I ask for are bullet points for evidence of exceptional ability. So it's, but like it's and these things can be like pretty off the wall. It doesn't need to be in the domain, the specific domain, but evidence of exceptional ability. So if somebody can like cite like even one thing, but let's say three things where you go wow wow wow, then that's a good sign.
But why do you have to be the one to determine that?
No, I
Presumably,
don't. I can't be. It's impossible.
Right.
But, I mean, total head count across the whole company is 200,000 people.
Right.
So,
But in the early days, what was it that you were looking for that couldn't be delegated in those interviews?
well, I guess I need to build my training set. So it's not like I have about 1,000 here. I would make mistakes,
Yes.
but then I'd be able to see where I thought somebody would work out well, but they didn't, and then why did they not work out well, and what can I do to, I guess, RL myself
Yes.
to in the future have a better batting average when interviewing people.
Mm-hmm.
So and my batting average is still not perfect, but it's very high.
What are some surprising reasons people don't work out?
Surprising reasons.
Like they don't understand technical domain, et cetera. But like,
No,
you've got like the long tail now of like, I was really excited about this person. It didn't work out. Curious why that happens.
Yeah. So generally what I tell people, or tell myself, I guess aspirationally, is don't look at the resume. Just believe your interaction.
Mm.
So if the resume may seem very impressive, and it's like, wow, the resume looks good, but if the conversation after 20 minutes is that conversation is not wow, you should believe the conversation, not the paper.
I feel like part of your method is that, there was this meme in the media a few years back about Tesla being a revolving door of executive talent, whereas actually I think when you look at it, Tesla's had a very consistent and internally promoted executive bench over the past few years. And then at SpaceX, you have all these folks like Mark Jankosa and Steve Davis and...
Steve Davis runs Boring Company.
No, now, but Bill Riley and folks like that. And it feels like part of has worked well is having very capable technical deputies. What do all of those people have in common?
The Tesla's sort of senior team at this point probably got average tenure of 10 or 12 years. It's quite long.
It's quite tenured.
Yeah. But there are times when Tesla went through extremely rapid growth phase, and so things were just somewhat sped up. And when a company, as you know, a company goes through different orders of magnitude of size, people that who could help manage, say, a 50-person company versus a 500-person company versus a 5,000-person company versus a 50,000-person company.
Yeah, you group people.
Yeah, it's just not the same team.
Yes.
It's not always the same team. So if a company is growing very rapidly, the rate at which executive positions will change will also be proportionate to the rapidity of the growth, generally. Then Tesla had a further challenge where when Tesla had very successful periods, we would be relentlessly recruited from, like relentlessly. Like when Apple had their electric car program, they were carpet bombing Tesla with recruiting calls. It was engineers just unplugged their phones. Like it just.
I'm trying to get work done here.
If I get one more call from an Apple recruiter, but they're opening offer without any interview would be like double the compensation at Tesla. So we had a bit of the Tesla pixie dust thing where it's like, oh, if you hired a Tesla executive, everything's gonna be successful. And I've fallen prey to the pixie dust, thing as well, where it's like, oh, we'll hire someone from Google or Apple and they'll be immediately successful, but that's not how it works. People are people. There's not like magical pixie dust.
Yes.
So when we'd have the pixie dust problem, we would get relentlessly recruited, and then also Tesla being engineering, especially being primarily in Silicon Valley. It's easier for people to just they don't have to change their life very much.
Yes.
They can just get their commute's going to be the same.
Yeah. So how do you prevent that? How do you prevent the pixie dust effect where everyone's trying to poach all your people?
I don't think there's much we can do to stop it. But that's one of the reasons why Tesla, they're really being in Silicon Valley, um, and and having the pixie dust thing at the same time meant that there was just a very, very aggressive recruitment.
Presumably being in Austin helps then.
Austin, yeah, it still helps. I mean, Tesla still has a majority of its engineering in California. So the you know, for getting engineers to move, I call it the significant other problem.
Yes.
So
So making others have jobs. Yeah.
yeah, exactly. So for Starbase, that was particularly difficult,
Yes.
since the odds of finding a non-SpaceX job
In Brownsville, Texas. But
pretty low. Yeah,
Yeah.
it's quite difficult. I mean, it's like a technology monastery sort of
Yeah.
thing. Remote and mostly dudes.
but again, if you
It's
go
not much
back,
of an improvement over SF.
Yeah.
if you go back to these people who really been very effective in a technical capacity at Tesla, at SpaceX, and those sorts of places, what do you think they have in common, other than, like, is it just that they're very sharp on the rocketry or the technical foundations, or do you think it's something organizational? It's something about their ability to work with you? Is it their ability to be flexible but not too flexible? What makes a good sparring partner for you?
I don't think it was a sparring partner. I mean, if somebody gets things done, I love them, and if they don't, so it's pretty straightforward. It's not like some idiosyncratic thing. If somebody executes well, I'm a huge fan, and if they don't, I'm not. But it's not about mapping to my idiosyncratic preferences. I'll certainly try not to have it be mapping to my idiosyncratic preferences.
Mm-hmm.
So yeah. Yeah, but generally, I think it's a good idea to hire for talent and drive and trustworthiness. And I think goodness of heart is important. I'd weighted that at one point. So, like, are they a good person, trustworthy, so smart, talented, and hardworking? If so, you can add domain knowledge. But those fundamental traits, those fundamental properties, you cannot change. So most of the people who are at Tesla and SpaceX did not come from the aerospace industry or the auto industry.
What has most had to change about your management style as your companies have scaled from 100 to 1,000 to 10,000 people? You're known for this like very micromanagement, just getting into the details of things.
Nano management, please. People management. Femto management.
So you're saying
We're going to go all the way down to Planck's constant. All the way down to Heisenberg's and Sydney principle.
yeah. Well, how do you? I mean, are you still able to get into details as much as you want? Would your companies be more successful if they were smaller? Like, how do you think about that?
Well, because I have a fixed amount of time in the day, my time is necessarily diluted as things grow and as the span of activity increases. So, it's impossible for me to actually be a micromanager, because there's that would imply I have some like thousands of hours per day. It is a logical impossibility for me to micromanage things. So now there are times when I will drill down into a specific issue, because that specific issue is the limiting factor on the progress of the company. But the reason for drilling into some very detailed item is because it is the limiting factor. It's not arbitrarily drilling into tiny things. And like I said, obviously, from a time standpoint, it is physically impossible for me to arbitrarily go into tiny things that don't matter, and that would result in failure. But sometimes the tiny things are decisive in victory.
Famously, you switched the Starship design from composites to steel.
Yes.
And you made that decision. Like that
Correct.
wasn't people were going around. They're like, oh, we found something better, boss. Like that was you encouraging people to get some resistance. Can you tell us how you came to that whole composite steel switch?
Yeah, so desperation, I'd say. The Originally, yeah, we were going to make Starship out of carbon fiber, and carbon fiber is pretty expensive. Like the you can generally when you do volume production, you can get any given thing to start to approach its material cost. The problem with carbon fibers is that material cost is still very high. So it's about 50 times, particularly if you go for a high strength specialized carbon fiber that can handle cryogenic oxygen. It's like called roughly 50 times the cost of steel. And at least in theory, it would be lighter. People generally think of steel as being heavy and carbon fiber as being light. And for room temperature applications, like say more or less room temperature applications like a Formula One car, static aerostructure or any kind of aerostructure really you're gonna probably be better off with carbon fiber. Now the problem is that we were trying to make this enormous rocket out of carbon fiber, and our progress was extremely slow.
And it had been picked in the first place just because it's light.
Yes. Like at first glance, like most people would think that the choice for making something light would be carbon fiber. Now the thing is that when you make something very enormous out of carbon fiber, and then you try to have the carbon fiber be efficiently cured, meaning not room temperature cured, because you've got sometimes you got like 50 plies of carbon fiber, and carbon fiber is really carbon string and glue, and you in order to have high strength, you need an autoclave, so something that's essentially a high pressure oven. And if you have something that's a gigantic, the oven's got to be bigger than the rocket. So we'd be trying to make the autoclave that's bigger than any autoclave that's ever existed, or do room temperature cure, which takes a long time and has issues. But the fundamental issue is that we're just making very slow progress with carbon fiber.
I think the meta question is why it had to be you who made that decision. There's many engineers on your team.
Yeah, how did the team not arrive at steel?
Yeah, exactly. Like, this is a part of a broader question, like understanding your comparative advantage at your companies.
It was because we were making very slow progress with carbon fiber. I was like, okay, we better try something else. Now, for the Falcon 9, the primary airframe is made of aluminum lithium, which is a very, very good strength to weight. Actually, it has about the same, maybe better strength to weight for its application than carbon fiber. But aluminum lithium is very difficult to work with. In order to weld it, you have to do something called friction stir welding, where you join the metal without it entering the liquid phase. So it's kind of wild that you could do that, but with this particular type of welding, you can do that. But it's very difficult to let's say you want to make a modification or attach something to aluminum lithium. You now have to use mechanical attachment with seals. You can't weld it on. So I want to avoid using aluminum lithium for the primary structure for Starship, and there was this very special grade of carbon fiber that had very, very good mass properties. So with rocket, you're really trying to maximize the percentage of the rocket that is propellant, minimize the mass, obviously, and but like I said, we were making very slow progress, and as I said, at this rate, we're never going to get to Mars. So we better think of something else. I didn't want to use aluminum lithium because of the difficulty of friction stir welding, especially doing that at scale. It was hard enough at 3.6 meters in diameter, let alone at 9 meters or above. it's like, well, what about steel? And so now I had a clue here because some of the early U.S. rockets had used very thin steel. The Atlas rockets had used a steel balloon tank. So it's not like steel had never been used before. It actually had been used. And when you look at the material properties of stainless steel, especially if it's been very like full hard, strain hardened stainless steel at cryogenic temperature, the strength weight is actually similar to carbon fiber. So if you look at if you look at the material properties at room temperature, it looks like the steel is going to be twice as heavy. But if you look at the material properties at cryogenic temperature of full hard steel, stainless of particular grades, then you actually get to a similar strength weight as carbon fiber. And in the case of Starship, both the fuel and the oxidizer are cryogenic. So for Falcon 9, the fuel is rocket propellant grade kerosene, basically pure, like a very pure form of jet fuel, which is but that is roughly room temperature. Although we do actually chill it slightly below. We chill it like a beer.
Delicious.
Yeah, we do chill it, but it's not cryogenic. In fact, if we made it cryogenic, it would just turn to wax. So, but for Starship, it's liquid methane and liquid oxygen. They are liquid at similar temperatures. So basically, almost the entire primary structure is at cryogenic temperature. So then you've got a 300 series stainless that's strain hardened, because it's at almost the whole thing's at cryogenic temperature, actually has a similar strength to weight as carbon fiber, but costs 50 times less than raw material, and is very easy to work with. You can weld stainless steel outdoors. You could smoke a cigar while welding stainless steel. It's very resilient. You can modify it easily. If you want to attach something, you just weld it right on. So very easy to work with, very low cost, and now, like I said, at cryogenic temperature, similar strength to weight to carbon fiber. Then when you factor in that we have a much reduced heat shield mass, because the melting point of steel is much greater than the melting point of aluminum. It's about twice the melting point of aluminum, and
So you can just run the rocket much hotter.
yes. So especially for the ship, which is coming in like a blazing meteor, it is you can greatly reduce the mass of the heat shield. So you can cut the mass of the windward part of the heat shield maybe in half, and you don't need any heat shielding on the leeward side. The net result is actually the steel rocket weighs less than the carbon fiber rocket, because the resin in the carbon fiber rocket starts to melt. So basically, carbon fiber and aluminum have about the same operating temperature capabilities, and whereas steel can operate at twice temperature. I mean, these are very rough approximations. People will.
I won't build a rocket base.
What happens is, like, people will say, "Oh, he said it's twice. It's actually 0.8." Oh, shut up, asshole.
Then that's what the main comment's going to be about.
God damn it. Okay. So the point is, actually, in retrospect, we should have started with done steel in the beginning. It was done not to do steel.
Okay, but to play this back to you, what I'm hearing is that steel was a riskier, less proven path, other than the early US rockets, versus carbon fiber was like a worse but more proven out path. And so you need to be the one to push for, hey, we're going to do this riskier path and just figure it out. And so you're fighting like a sort of conservatism in a sense.
That's why I initially said, like, the issue is that we weren't making fast enough progress. We were having trouble making even a small barrel section of the carbon fiber that didn't have wrinkles in it. So because at that large scale, you have to have many plies, many sort of layers of the carbon fiber. You've got to cure it, and you've got to cure it in such a way that it doesn't have any wrinkles or defects. The carbon fiber is much less resilient than steel. It has it's less toughness. So like stainless steel will stretch and bend, and the carbon fiber will tend to shatter. So toughness being the area under the stress strain curve, so that you're generally going to have to do better with steel. Stainless steel, to be precise.
One other Starship question. So I visited Starbase, I think it was 2 years ago, and went with Sam Teller, and that was awesome. It was very cool to see in a whole bunch of ways. One thing I noticed was that people really took pride in the simplicity of things, where, everyone wants to tell you how Starship is just a big soda can, and we're hiring welders, and if you can weld in any industrial project, you can weld here. But there's a lot of pride in the simplicity, and
practically Starship is a very complicated rocket.
So that's what I'm getting at. Are things simpler or are they complex?
I think maybe just what they're trying to say is that you don't have to have like prior experience in the rocket industry to work on a Starship. Somebody just needs to be, smart and work hard, and be trustworthy, and they can work on a rocket. They don't need prior rocket experience. Starship is the most complicated machine ever made by humans, by a long shot.
In what regard?
Anything really. I'd say that there isn't a more complex machine. I'd say that there's pretty much any project I can think of would be easier than this, and that's why no one has made a rapidly reusable. Nobody has ever made a fully reusable orbital rocket. It's a very hard problem. Many smart people have tried before, very smart people, with immense resources, and they failed. And we haven't succeeded yet. Falcon is partially reusable, but the upper stage is not. Starship version 3, I think this design that it can be fully reusable, and that full reusability is what will enable us to become a multi-planet civilization.
Can you say what the
any technical problem, even like a hadron collider or something like that, is an easier problem than this.
We spent a lot of time on bottlenecks. Can you say what the current Starship bottlenecks are, even at a high level?
Trying to make it not explode. Generally.
That old chestnut.
Really wants to explode.
All those combustion materials.
We've had 2 boosters explode on the test stand. One obliterated the entire test facility. So it only takes like one mistake, and the amount of energy contained in a Starship is insane.
And so is that why it's harder than Falcon? It's because it's just more energy?
It's a lot of new technology. It's pushing the performance envelope. The Raptor 3 engine is a very, very advanced engine, by far the best rocket engine ever made. But it desperately wants to blow up. Just to put things in perspective here, on liftoff, the rocket is generating over 100 gigawatts of power. It's 20% of US electricity. So
Actually, it's insane.
It's a great comparison.
while not exploding.
Sometimes.
But sometimes, yeah. So how does it not explode? There's thousands of ways that it could explode, and only one way that it doesn't. So we want it to not merely not explode, but fly reliably on a daily basis, like once per hour. And obviously, if it blows up a lot, it's very difficult to maintain that launch cadence.
Yes.
And then I'm gonna say like what's the single biggest remaining problem for Starship? It's having the heat shield be reusable, that such that no one's ever made a reusable orbital heat shield. So the heat shield's got to make it through the ascent phase without shucking a bunch of tiles, and then it's going to come back in and also not lose a bunch of tiles or overheat the main airframe.
And isn't that hard? Because it's kind of fundamentally a consumable.
Well, yes, but your brake pads in your car are also consumable, but they last for a long time.
Fair. Okay.
So it just needs to last for a long time. That's it. Just I mean, we have brought the ship back and had it do a soft landing in the ocean. I've done that a few times, but it lost a lot of tiles. You know, it was not reusable without a lot of work.
On to part 9.